Okay. Hi, guys. Welcome to the class. Hi, Janvi. Welcome to the session. Let everyone join and then we're going to get started. Meanwhile, see, we have already covered in vector algebra. In the previous session, we have already covered concepts about scalar product and vector product, which is the dot product as well as the vector product, which is also called as cross product. That is something which you have covered. We covered the properties of that in the previous session. If you've not seen that yet, please see it once so that you're going to get a fair idea about what sort of questions you might get in your JEE in terms of the concepts related to those two particular areas, which is the dot product as well as the cross product. In today's session, we'll primarily be talking about scalar triple product and vector triple product, or the vector product of four vectors, you may say. So that's what the primary concept of the class would be today. Okay. Meanwhile, I'll just sort of wait for some more people to join. Then we're going to get started. Janvi, I hope you're here. All right. So, yeah, people are now sort of joining. Hi, Janvi. All right, so let's get started without any delay. So first of all, what I'll do is just quickly go through a few important bits of scalar triple product. Then I'll pick a few JEE questions which came. In fact, there was one question in JEE Advanced 2018, the last year's ones, wherein the scalar triple product is being used a bit. So we'll talk about that as well. So let's see. Hi, Anand. Welcome to the session. So first of all, I have all the properties with me on board. So just quickly go through them once, one by one. So let's see over here. We already know what is scalar triple product and how is it being represented. It's being represented in this form. This is how we represent scalar triple product, and this is how we expand it. A dot B cross C. Now this can also be written as B cross C dot A, or you can change the order. It will move in a cyclic order. A, B, C, it will move in the same cycle. You can choose any component anywhere, right? The sequence will remain the same. We all know about it. What do I mean by that? ABC will be equal to BCA will also be equal to CAB. But as soon as I sort of switch any two, if I replace BC, if I change their position, I need to introduce a negative sign in front of it. This is how scalar triple product works. And if I want to expand it, if it's being given to us in a vector form in terms of ijk, this is how we can expand it in determinant form. So over here, we'll just write down the components of A, B, and C vectors, and then take the determinant to calculate the scalar triple product of these three vectors. Geometrical interpretation is very simple. The geometrical interpretation of scalar triple product is that it defines the volume of a parallelepiped, right? Parallelepiped is a kind of cuboid at times, or it can be a parallelogram sort of cuboid, okay, with a parallelogram base maybe. So the volume of parallelepiped wherein A, B, and C are coterminous edges. A, B, and C are coterminous edges, right? So these are coterminous edges, or the vectors which define the coterminous edges. So the scalar triple product of these three vectors are said to be the volume of the parallelepiped. For instance, if I sort of draw a parallelepiped, it would look somewhat like this. Most of you already know about it. It is just a quick revision. Meanwhile, others will also join. So I'll say if this is vector A, this is vector B, can be co-initial or coterminous, doesn't matter. And this is C, then the volume of the parallelepiped will be the scalar triple product of these. Now, very important properties of scalar triple product. Few important properties which you must remember because they can be directly tested and used in JEE examination. I'll show you a few examples wherein you can sort of see these things happening. So if three non-zero vectors A, B, C are there, and if they are coplanar, they will be coplanar if, so this is the necessary as well as the sufficient condition. So if and only if ABC is equal to 0, the STP of ABC, the scalar triple product of ABC is equal to 0. Most of you already know about it. However, you should also remember that if either of these, either all three or at least one pair out of these three vectors are parallel, in that case, also the scalar triple product turns out to be equal to 0, because if at least one of the pairs is parallel, we can say all of them are coplanar. So you can sort of put a note point over here stating that if I've been given AAB, the scalar triple product will be equal to 0. Or if I've been given BBC, in this case, the scalar triple product is also 0. All right. And this is again important. Most of us tend to forget this because you don't find many questions. However, this is an important bit. If A, B, C are three mutually perpendicular vectors, in that case, the scalar triple product will always be either 1 or -1. For example, if I'm saying scalar triple product of I, J, and K, where I, J, K are unit vectors along X, Y, and Z axis. So this is 1. If I change the order, saying K over here and J over here, this turns out to be -1s. This is also an important result which we must remember. Then these results are also kind of utilized in different questions. A minus B, B minus C, C minus A. These are three vectors. Obviously, these are vectors, placed vectors on top of it. So you can sort of place it. So these are vectors. So the difference of each pair, if I take the scalar triple product of these three vectors, which are formed by the difference, the scalar triple product will be equal to 0. Similarly, if I form the scale, or if I want to find out the scalar triple product of these three vectors in terms of A, B, and C, and I'm adding them, that turns out to be twice of A, B, and C. That's double the scalar triple product. These are two very obvious ones, which we all sort of remember. This is also an important one, right? Very important one. We'll see one question based on this as well. So if I'm multiplying two scalar triple products is what? It's just a number. So if I multiply these two numbers, I'll get a different number, which can be written in the form of the determinant in this form. So it'll be A dot L. So you just need to take the dot between this, this, and this. You can mention it either in a column or in a row. Similarly, you can take the dot product between these. You can mention it in a column or in a row, right? And similarly, the last one. So this is how we practically multiply two scalar triple products. This is again an important one. If any of the vectors is given to us as the sum of three vectors which are non-coplanar, so LM and N are non-coplanar, here are non-coplanar. They are not coplanar vectors. So in that case, what we can say is that the scalar triple product of A, B, C will be the determinant formed by the components over here of L, M, and N with respect to A, B, and C, right? And then we will multiply it by the scalar triple product of L, M, and N. This was just a short summary of whatever you need to know in scalar triple product. Let's sort of see a few questions based on that. The very first question there on board, a very, very simple question. The number of distinct real values of lambda for which the vectors this are coplanar. You know, as soon as the question says that the vectors are coplanar, the scalar triple product must be equal to 0. So over here, you will calculate the scalar triple product. For that, you will calculate the determinant. You will just choose the components. It will be minus lambda square from here, 1 from here, 1 from here. This is from the first vector. From the second vector, we get 1 minus lambda square in 1, 1 minus lambda square in 1. And from the last one, it will be 1, 1 lambda, negative lambda squared. So this scalar triple product must be equal to 0. If I want to solve it, it's simple. It's just a determinant. So we'll be able to solve it very quickly. We can see one thing that we can add all the rows and we'll get that stuff outside. So we can take 2 minus lambda square as common. We'll get a 1, 1, 1 over here. 1 minus lambda square, though you can directly calculate the determinant as well. However, this will break everything into factorized form. So it'll be simple for us to identify it. Now, if you see, we can again subtract the rows. From the second row, we can subtract the first one. From the third one, we can subtract the first one. This will be the best method in my opinion, Suraj. So I hope this would work with you as well. So over here, this will be 0. This will be 0 minus lambda squared minus 1. Right? And then you will be able to find out the simple format. So it is negative of negative will get positive primarily, or this is lambda square plus 1 whole squared is equal to 0. We can see that this is equal to 0. This can happen only when lambda square is equal to 2. Only when lambda square is equal to 2. Therefore, the value of lambda turns out to be square root of plus minus the square root of 2. So that's all what we sort of need to do over here in order to figure out the distinct values of lambda for which this turns out to be coplanar. Okay, look, if they are coplanar, you can also say that they are linearly dependent on each other. Therefore, one can be expressed as the sum of others. And you can also compare the coefficients of, the components of I, J, and K, and then you can sort of get down to the answer. That is also a way which you can apply. However, this is a way which fits in every question. That's why it's preferred for you to take this route up whenever coplanarity is being taken into consideration. You could have also said that one of the, vector can be expressed as the sum of the other two vectors with some scalar in between, and then you can sort of you need to find out that scalar value as well. That will just take a little extra time to solve the question. I hope this question is clear to all of us. What was the basic bit of, or the basic use of scalar triple product. Let's see one more question, 1998, way back. However, such questions are also kind of frequent if you see scalar triple product uses in IIT JEE. So if these are the three vectors given to us, they are linearly dependent vectors. Now, remember, I would sort of give you a point to remember. Three vectors are linearly dependent. LD defines as linearly dependent, implies three vectors which are linearly dependent implies they are coplanar. They are coplanar. Obviously, if I'm saying three vectors, three non-zero vectors. They are coplanar. They must be coplanar. So you can express one as the sum of the other two with a scalar in between, right? So then we can say that they are coplanar. So you can remember that. So over here, because the question says these three vectors are linearly dependent vectors, therefore we can say that the scalar triple product of these three must be equal to 0 as they are coplanar. So we will be calculating A, B, and C, which is sort of easy to calculate because that's just the value of the determinant 1, 1, 1, 4, 3, 4, and 1 alpha beta. This is what the scalar triple product is. This must be equal to 0 over here as the vectors are coplanar. So we need to solve and figure out the value of alpha and beta over here. Let's quickly solve this. So you can either use your difference form. So 1, 0, 0, 4 and 1, 3 minus 4 gives me 1, 4 minus 4 gives me 0. This is alpha minus 1, and this is beta minus 1. Right? Pranav, I hope you know about how to solve determinants. I'm just using a simple analogy, or basically a simple transformation. R2 is being replaced by R2 minus R1, and R3 is being replaced by R3 minus R1. So I'm subtracting the first, column. I am doing it by column. So I am subtracting, mentioning the second column as second column minus first column, and the third column as third column minus the first column. And then this turns out to be beta minus 1 times alpha minus 1 times 1 is equal to 0, which means alpha and beta. So, this is 0. This is 0. I'm so sorry. So this just gives us beta minus 1 is equal to 0, right? Just gives us beta minus 1 is equal to 0, which implies beta is equal to 1. Now, if I check out the options, there is just one of the option that contains beta is equal to 1. So you can sort of directly mark it as the answer. However, if you want to find out the value of alpha as well, so what you can do, or what you need to do is, over here, you need to utilize this, right? Minus 1 aiga, minus 1 where? Yeah, this is sort of minus 1. Thank you. So 3 minus 4 and 4 minus 4. This is minus 1. However, it will not make any difference over here. However, thank you. So for the sake of recalling that. So over here, this is root 3. We know about it. And magnitude of the third vector, vector C, can be written as 1 plus alpha square plus beta square, which is root 3 whole squared. Just taken square on both the sides. I hope I've mentioned it correctly. Yes, we already know what is beta. Beta is 1. So we can calculate the value of alpha square. 3 minus 2, that is 1. Hence, alpha turns out to be plus minus 1. We have already got our answer, though. We can sort of mark it directly. Okay. Okay, now this is a question, last year's question, simple question. You just need to have a clarity, and trust me, guys, it's important for you to construct or at least think of what sort of figure will we get. At least that makes us at a comfortable stage that we know what the question is talking about. So if I see this question, the question says let A and B be two unit vectors. Fine enough, they're unit vectors. Lokesh, probably your internet speed might not be up to the mark. So A and B are two unit vectors such that A dot B is equal to 0 for some xy that belongs to R. Yes, Pranav, you can directly expand the determinant without using the property. So for some xy that belongs to a real number. C is given to us as sum of these two vectors A and B plus the cross product of vector A and vector B. The magnitude of C is also given to us as 2, and the vector C is inclined at the same angle alpha to both A and B. Now if you see, C is a vector that is formed by the sum of A and B plus A cross B. Now we know A cross B is a vector perpendicular to the plane. This is a vector perpendicular to the plane of A and B, of vector A and B. So basically vector C will basically be in some other plane. If this is vector A and this is vector B, both are kind of perpendicular to each other. Why perpendicular? Because A dot B is equal to 0. So they must be perpendicular to each other. Then there is a vector C. There is a vector C somewhat aligned like this, which forms an angle alpha from this plane. So basically it forms the same angle from B as well as from C. I hope this makes sense. So C is basically one of the vectors of this sort. Anyways, this was just a way to kind of understand what the scenario is being given to us. However, it was not required for you to make the diagram. So now the question is asking for 8 cos square alpha. Alpha is what? Alpha is the angle between A and C and A and C and B and C. So what we know is vector C is XA YB plus A cross B. Over here, what we can very easily identify is that A and B, they are 90 degree. A dot B is equal to 0. Vector A and B, the angle between them is 90 degree. And what else we can do is A and B are unit vectors. So we can sort of figure out what is A dot C and what is B dot C. So if I take the dot product of C and A, what will I get? So I'll say A dot C will basically be equal to X times A dot A plus Y times A dot B plus A dot A cross B. I hope all of us know that this bit turns out to be 0. Yeah, this turns out to be 0. This is given to us as 0, so this will also turn out to be 0. A into A is, A dot A is just A squared, and A is a unit vector, so that is 1. Hence, A dot C, which is nothing but AC cos alpha, AC cos alpha, obviously the magnitudes, is equal to X. A is a unit vector, C's magnitude is 2. So X is basically twice of cos alpha, right? Similarly, what we can say is we can take the dot product with B over here. So what will we have? X times 0 plus Y B dot B will give me 1 plus over here B dot A cross B. B and B are again parallel vectors, hence this will also be 0. So therefore over here we can also say that 2 cos alpha, this is what we're going to get, 2 cos alpha, because B is a unit vector, magnitude 1. C is a vector that has magnitude 2, and the angle between them is alpha. So this turns out to be Y. So X is 2 cos theta, Y is 2 cos theta. That implies X and Y both are equal and equal to 2 cos theta, which is a simple stuff. However, we don't have to find out what is 2 cos theta. We need to find out what is 8 cos square theta, and that must be a number. So now we have figured out B dot C and A dot C. Let's also find out C dot C. So C dot C, let me choose a different color so that it's more visible. I talk about C dot C. So this is what we have. We'll take the dot with the same. And you already know how to sort of expand it. Right, if I'm taking the dot, I'll take the dot between this and this, I'll get x squared over here. this and this, A dot B will make it 0. Right? If I'm multiplying this and this, A dot B will make it 0. If I'm multiplying this and this, A and A are parallel vectors. Again, this will be equal to 0. This into this, A dot B equal to 0. This into this will give me y squared. B dot B is basically 1. We know about it, y squared. And this, when multiplied by this, again 0. Similarly, this multiplied by this will be 0 because A and A are parallel vectors. Scalar triple product. In scalar triple product, if two of the vectors are parallel, the result is 0. Over here, B and B are parallel, result 0. Over here, we'll take the square of the magnitude. This is how we can sort of express that, right? So this is what, this is basically determinant of C whole squared, determinant of C, sorry, the magnitude of C was 2. So this is 4. X square is 4 cos square alpha. Y square is 4 cos square alpha. And over here, A cross B is A, B sine theta, wherein the angle between them you have already calculated is 90 degree because A dot B was equal to 0. And it's just a magnitude, so we'll not multiply it by its unit vector. So I'll take the square of that. However, this is 1. This entire thing is 1. 1 squared is 1. So from here, we can get 8 cos square alpha plus 1 is equal to 4, or 8 cos square alpha turns out to be equal to 3. Obviously, it's an advanced question, so you need to involve a little bit time in calculation. However, I hope this makes sense to all of us. This is how we're going to be doing this question. A simple one. Very simple one, in fact. All right, so one more question on the same, and then we'll move on to vector triple product. The edges of a parallelepiped are of unit length and are parallel to non-coplanar unit vectors. This is this. Fine enough. So the edges are being given to us. So let's say this is, oops. Let's say this is your parallelepiped, and so these are the edges being given to us. This is being given to us as unit vector A. It is along these vectors. This is along B and this is along C. These are the 3 edges which we have. Therefore, we can say the volume of the parallelepiped will be the scalar triple product of A, B, and C. Obviously, A, B, C are unit vectors. So scalar triple product of these 3 unit vectors. A, B, and C. Unit length are parallel to this. Now, what's being given to us is A dot B, B dot C, C dot A. That's being given to us as half. We don't know how to express this in terms of it. However, we know very good bit that where A dot B and B dot C and C dot A was considered. See, I'll just give you or show you that board. I have given it to you over here. If you see it over here, right? I can multiply this, I'll get something in terms of dot, something in terms of the dot product of the given 2 vectors. This is what I'll be using over here. I'll say a better way out of solving this is that I can say, take or multiply these 2 scalar triple products with each other, right? To get A dot A, I'm writing it directly, A dot A, A dot B, A dot C, B dot A, B dot B, B dot C, C dot A, C dot B, C dot C, right? You've been given that A, B, C are all unit vectors. It's being given to us as unit vectors of unit length. Obviously, A dot B, B dot C, C dot A are half. A dot A, B dot B, and C dot C will turn out to be 1 because they are unit vectors. So this turns out to be 1, half, half. This is half, 1, half. This is half, half, 1. Just need to solve this determinant. After solving this, you will get the result to be half. So from here, you can say that the square of the scalar triple product is basically half. Therefore, the scalar triple product of A, B, and C will basically be 1 upon square root of 2. Hence, the answer to the question is 1 upon square root of 2. That's A. So this is how we can sort of calculate the answer to the given question, which is the volume of the parallelepiped. Obviously, volume can't be negative, so we'll not say minus 1 upon root 2. Don't do that, please. Okay, hopefully this makes sense to all of us how to go about this question. Now, if I talk about vector triple product, see, if I talk about vector triple product, we all know Just for the sake of quick revision of the formulas, A cross B cross C, right? So this vector triple product is being expanded in what form? We take the dot between A and C, we get a scalar. So this is scalar. We multiply it by vector B. So it's basically B is being amplified to A dot C minus A dot B times C. So this gives us the vector difference of vector B and C when they are being multiplied by some scalar. So it is basically a vector which is the difference of vector B and vector C when they are being multiplied by two scalars, A dot C and A dot B. All right, so this is kind of simple for us to gauge. Next thing over here, one of the important properties over here is A cross B, B cross C, C cross A. Just remember this is ABC whole squared. Whatever we just did a moment back, the determinant one, this is also equal to A cross B, B cross C, C cross A. This is actually one of the questions, but it's good to remember this as a result. You can also figure out the vector product of four vectors. If I'm saying A cross B cross C cross D, so you can kind of assume this to be some vector P, maybe some vector P, because this will basically be a vector only. And then you can apply the scalar triple product between these two vectors. So it'll be P dot D times C minus P dot C times D. And then you can replace the value of P. So A, B, and D. That is basically the scalar triple product of ABD, scalar triple product of ADB. And over here, if I replace P as AB, so I'll get ABC, this STP of these three products. So this is how we can expand the vector product of four vectors. Very simple analogy. Let's see one more question on it. If ABC are three vectors such that this is equal to this cross vector triple product of three vectors. So if B is not parallel to C, then angle between A and B is what? Okay. So what can we say, or what can we see over here is, look, what we know is A cross B cross C. We know the expansion to it. This is being given us as root 3 upon 2B plus C. We know the expansion to it. So this is, obviously these are unit vectors. So you should write it as unit vectors only. This is what we can get. This is root 3 upon 2 V, B, and root 3 upon 2 vector C. So from here on comparison, what we can say is A dot C is equal to root 3 by 2 and A dot B is equal to negative root 3 by 2. A, B, and C are non-parallel. Okay, we need to figure out the angle between A and C. Okay, A and C, we need to figure out the angle between them. We can very easily find out the angle because that will basically be cos of theta. These are unit vectors. It'll give me 1 cos theta is equal to negative root 3 by 2. When will it be negative root 3 by 2? When theta is equal to 5 pi by 6. Pi minus pi by 6. Pi minus pi by 6 is the answer to the question. I hope this makes sense to all of us. So fine enough, that's all what we have for us today. I hope you can remember all these properties. Good luck for your exam. If you want to sort of see more, remember more, and do more, try and see all our previous lectures. Try and sort of see what sort of questions might appear in your JEE examination. Good luck for the exams, guys. Take care. Have fun. Good night. And have a good day, in fact, I must say.